So today we'll finish up on the causal values induction, and we are going to go to the new topics, which is semantics of propositional logic. But before we do that, I want to review some materials that maybe you have seen this before somewhere in high school or maybe some other courses in CS. But I want you to be make sure that you understand this concept well, because this will repeat on and on throughout the rest of the semester. So I'm going to talk about what is a set, what is a subset, what are the set operations, what are the Cartesian product relations and functions, and there's some class of functions, one-to-one function, one-to function, one-to-one correspondence. So we are going to study those. So last time we were starting to prove some properties of propositional formulas. And the propositional formulas are defined in a recursive way. So to prove these properties of some mathematical object that has recursive definition, we use the induction. So induction is kind of, it reflects the same structure as what you build in a recursive way. So to note that the first two cases are like a base case. You have an every atom or a bottom or top. They become the formula. And if you have a formula F, or somebody give you formula F, and then you can build another formula using third and fourth bullet, you can use negation symbol, or you can use binary connective. Okay. So to prove this property, you have to first identify what is the P of F. So P of F is the properties of the formula that F has. Now note here that this is a bit different from the other induction that you saw in the previous classes. The induction was based on the numbers. Okay, so postage example and horse example and Fibonacci numbers, they were about the numbers. Here we turn our attention to the formulas. So formulas are these parameters for this P. So we're talking about the formulas, properties of formula F. But formulas are also built recursively. So it is built based on the smaller formulas. So some sub-formulas, and you can make a bigger and bigger formulas. So it is actually applying the same idea of induction as in the numbers. So these are the four cases that you have to show for all such formulas. So the first thing is, if you want to show any property for any formula, so you have to show that this property holds for the atom P and for the zero-place connectives. Okay? And if you have other things like the binary connectives and disjunction, you have for conjunction disjunction, you have to use the third and fourth cases. Okay, now, in these cases, you have induction hypothesis that the formula F has the property P, or formula G has the property P. Using this, you're proving the same property for the next formula, which is not F, or the formulas F sun G. Okay? So, again, don't argue with induction hypothesis. There's no use for doing that. But once you assume that, can you prove the next case holds? That's the idea of induction. And we saw the first proof in this style, which was to show that for any formula, you have same number of left and right parentheses. And how do we prove this? First, we identify the property that P of F means this one, L of F is equal to R of F. This is mathematical notation that helps us to prove easily. Okay? So you can write in English, but this is actually easy to manipulate. Okay, so case 1, case 2 is actually easy because there are no parentheses. So this can be easily checked by looking at this number of left parentheses and right parentheses are 0. Case 3, you assume that for given F, whatever the formula F, you don't know exactly, but you know for sure that the number of left parentheses and right parentheses there in F are the same. So that is what you assume. You don't argue with this, but you're trying to prove this based on that assumption. Okay? So how do you prove this? So L of not F. Basically, we have to go all the way through until here, R of not F. So this is the goal that you have to prove, and this is the middle part that you have to proof. So how do we prove those things? If you count number of left parentheses in here, you know that it should be 1 plus whatever the number of left parentheses there. So it's 1 plus LF is the total number of left parentheses in this string. Okay, okay, so this string. And since we know that L of F is equal to R of F, that was our induction hypothesis, we can algebraically manipulate that 1 plus L of F is equal to 1 plus R of F. And this number is actually the same as the number of right parentheses in this string. Okay? So, whatever the number of right parentheses in F plus 1. Okay? Now, case 4 is similar, but you have actually two induction hypotheses. Because this is course of values induction, you can use induction hypothesis for whatever formula that is smaller than the current formula that you are going to prove. Among them, you chose next largest formula, which is F and G. So for F, you know that number of left and right parentheses are the same, number of left and right in G are the same. So from this, can we prove that the number of left parentheses here is equal to number of right parentheses here? Okay? So how do we find the number of left parentheses? So this is the first one. So this is 1 here. And F, you may not see it, but there are some number of left parentheses. So we can denote that by L of F. Same as G as L of G. Okay? So this is the number of all left parentheses in this string here. Same way, this is the number of right parentheses. So this L of F is same as R of F. L of G same as R of G. So you get this equation. And this whole sum is exactly the same as number of all right parentheses in this string, because that's R of F, R of G, followed by 1. That the total number of right parentheses in this string is this equation. So we prove in the end, this one is equal to this one, which was the goal to prove. After establishing these 4 cases by induction principle, you can say that this property holds for all formulas, because all formulas, whatever the formula is built using these rules. And these 4 cases cover any possible ways to form the formulas. Right, so now let's talk about sets, relations, and functions. Okay, so what is a set? Everybody knows what is a set. It's a collection of distinct elements. So if you have 1, 5, 7, this is one way to write the set. We write the members explicitly by comma-separated list. It's not a list, but it's, you use comma to separate this element. You can also write as in English, the set of all students in CSE 259. You can also talk about the set of all real numbers in 0, 1. Here, you cannot actually enumerate them because real numbers in 0, 1 are infinitely many. But it's not only infinite, you cannot count, uncountably many. Okay? And set of all positive integers is countable but still infinite. The set of all positive even integers, okay, that's also. If you learn the number theory, you'll see that the size of the 2 last sets are actually the same. Okay, so, but we are not going to that here. Another way to write it is you have this so-called intentional set notation. You write x bar and then give the property about x. The idea is the property is true, then this element should belong to the set. If the property is not true, that element will not belong to the set. So when they say x is an integer divisible by 2, only those numbers will be in the set. Okay? And if it is not divisible by 2, that will not be in the set. And we write membership as x is a member of A if x is an element of A. Okay? Now, the Socrative time. So actually, this is not. So 5 is a member of 157. True or false? True. Good. Because 5 is one of the comma separated one. So 8 is a member of 157. True or false? False. Okay. Good. So you know what is. Okay, so this is true. This is true. This is false. Now, what about this guy? So let's actually open the Socrative. Okay, so this is empty set. Empty set is a member of 157. True or false? Okay, so you don't surprise me. So one student who is not listening at all didn't participate anything here. But more, okay, I don't see it. Okay, so majority chose true. Is it? This is actually false. We can say 1 is a member, 5 is a member, 7 is a member, but empty set is not a member. Empty set is not an element of this set. If it was to be an element of the set, you should have seen empty set as one of the member in comma separated way, like this. In this case, we can say empty set is a member of this whole set. Empty set, in this case, is not a member of this set. Empty set is a member of this set. Okay, it's a bit tricky, but you have to be worrying about this nested level here. Okay, all right, so most of you got caught in my tricky question. Okay, what about the next one? So 157 is a member of 157. Again, if you look at the same way, 157 is not a member of this set 157. So this is actually false. And 70% of you got it right. So that's good. What about this one? So the last one is 1, an element of this set contains a singleton set 1. Okay, so majority answered correctly. This is not. Because if 1 is a member of the set, it should be like 1 is a member of 157. It should be one of the comma separated element. Okay, but this is not. Okay. Although we can say in the last case, the singleton set is a member of the set that contains a singleton. This is actually true. Okay, next one. Subset. Okay, so the subset, the reason that maybe some of you got wrong in the previous question is because you confused between membership and the subset. The subsets are the relation between two sets. And here, the idea is every member of A is also a member of B. Okay? And we also say proper subset, okay? Because if you just say in the first line, A and B could be the same. Okay? Even though we say A is a subset of B, A could be equal to B, and still A is a subset of B. So in order to distinguish that with A is smaller than B, we say A is a proper subset of B if A is a subset of B, but A is not equal to B. Okay? Or you can say B is not a subset of A. Okay? So now if you look at this, let's actually go one by one together. If the A, is it true or false? True or false? 2 is a subset of 2, 4, 6. False. Why is it false? 2 is not even a set. Yeah, that's a very good answer. Subset relation is defined between the two sets. Okay, 2 is not even a set, so this is false. Now, what about B? Let's do the substitutive here. Okay. So is empty set a subset of 2, 4, 6? And the idea is apply the definition that is given there. When you say one set is a subset of another, then every member that belongs to A is a member of B. Okay. So about 2/3 was saying true, okay, and 1/3 is saying false. The answer is actually true. Why is it true according to the definition? Well, how many elements does empty set have? Nothing. Okay? So then you don't have to worry about whether the element of A belongs to B because there's nothing to check. So this is very trivial to check. Okay. C. Is it true or false? 2, 4, 6. Is C true or false? True, false, true, false. If you say true, again that you're confused with membership. The membership is true. If it was not a subset relation, if it was a membership, it could have been true. But if it's a subset, it's not. This is false. And if you look at D, it will be easier. Okay? So look at the D first. D says every member of this set. So there, how many elements are in this set A? How many elements are there? How many? 3, right? So 2, 4, 6. These are the elements. Is 2 belong to the second set? Yes. Does 4 belong to second set? Yes. Does 6 belong to second set? Yes. All these 3 belong to second set. We are fine. So this is true. Okay? Now, let's look at this. How many elements are in 2, 4, 6? 3, same as before. Is 2 a member of this one? No. So this is not a subset relation. What about this? How many elements are in this set? How many elements are in this set? 1. The member itself is a set, 2, 4, 6. Does it belong to this set? No. This is also false. Okay? So the definition is not complicated, but applying the right definition is not that always simple. What I often observe is you're confused between the membership and the subset relation. So try to first identify what is the membership and use membership to check the subset relationship. If you can do this correctly, you will not fall into this trap. However, even if you do that, there is a problem. This is not your problem. Okay? So we just said, maybe in your high school or even in some discrete math, if you didn't learn this thing, you say that a set is a collection of any definable collection. Okay? This is actually not well defined. It's called naive set theory, and there's actually a well-known example about it, why this is a problematic definition. So if you just say set is just a collection of objects, that's not going to work in some formal mathematics. So Russell was giving this example. So there's an old village where there's only one barber, and they are all cleanly shaven. And the barber announces this fact that I shave all and only those men who do not shave themselves. Okay? I'm going to shave all and only those people who do not shave themselves. That's what he announced it. The question is, who shaved the barber? Why is it I don't know. Actually, this is not that simple. Okay? So let's try to see what is going on using natural deduction that we know. Okay? So who shaved the barber? How many cases are there? We are going to use OR elimination method. Yes, how many cases?
Are we assuming that the barber is a boy?
It's an old town, yes. It used to be, yes. Let's not make things more complicated than necessary. Okay? So barber is a man, okay? So how many cases are there? Actually, there are two cases, okay? Who shaves the barber? It could be barber himself, or it could be somebody else, okay? This is law of excluded middle, either barber or not the barber. Case one, suppose another person shaved the barber. What becomes a problem? If another one shaves the barber, barber is the one who does not shave himself, right? And according to what barber claimed, he has to shave himself because he didn't shave himself. Big case. Let's go slowly. Okay, so let's actually look at this claim, all part. Let's look at all part. Barber said, I shave all men who do not shave themselves. Okay? So let's look at this. So we ask a question, who shaved this barber? Case one, somebody else shaved the barber, meaning that barber is not shaving himself. Since barber does not shave himself, and he has to shave all those people, that means he has to shave himself. Doesn't make any sense. So this is a contradiction, because he said he is going to shave all men who do not shave. So if he does not shave himself, then according to his claim, he has to shave himself. A little bit tricky. If you didn't understand, just read it again and you may get it. Okay, case two. What if now the barber shaves the barber? And I want you to look at now this part of the barber's announcement. If barber shaved himself, then according to he said, he's shaving only those who do not shave himself. So he shouldn't shave himself. You get it? Now let's go slowly again. So suppose the barber shaved the barber. There's only one barber, so don't worry about different barbers. Okay. So barber shaved himself. But he said before, I shave only those men who do not shave themselves. So if he's shaving himself, he shouldn't shave, right? That's not going to work. Again, we get this contradiction. No matter what case that we are in, we got the contradiction. That means we conclude contradiction at the end using the law of excluded middle. So if I'm going to write it here, this is not barber or barber. This is the law of excluded middle. Case one is not the barber. We got the contradiction. Oops. Case two, if it is Barber, we got to also do contradiction. So this is the first box, second box. Okay, using the OR elimination, we can derive bottom at the end. Do you see the structure here? This or this must be true. If this is true, we got contradiction. If this is true, we got also contradiction, meaning that regardless of which case that we are in, we always get the contradiction. Okay? So what happens here? If you define, so the conclusion is, if you define the definition of set in this way, you will be in trouble. All mathematics will collapse because mathematics become unsound, which is the very property that every mathematician wants to avoid. Okay? You try to build some safety critical machine using all this mathematics, and then you realize that it has a bug in the mathematics, not your code. The theory itself has a bug. Okay. Okay, so what is going on with this approach to define a set? Basically, it's this definition that creates a problem. The set of all sets which do not contain themselves. Okay, if you just think about, instead of Barber, you can just think about a set. Okay, so here is the definition of the set that you can write if you accept the naive set theory. So let R be a set of elements such that X, a set of X such that X does not contain X. In other words, X is not a member of X. Okay? And if you remember the previous slide, we actually saw many examples of that kind. So for instance, 1, 5, 7, okay, was not a member of 1, 5, 7, right? So then this 1, 5, 7 will be in R. Okay? So this set, of course, is not well defined, but anyway, if you can accept the definition in naive set theory, we can say that this is a set. Okay, so R is a set of elements X such that X does not contain X. What happens here in the Barber's paradox is you will immediately realize that R is not a member of R if and only if R is a member of R. That was the contradiction that led to the Russell paradox. Let's actually look at this one more time. So suppose you can define this set. Okay, and let's assume we have an element that satisfies this relation. So R is not a member of R. Okay, like 157 was not a member of 157. Now let's look at the definition of R. R is saying that anything that does not contain itself must belong to R, right? Look at this. Okay, if R is not a member of R, then it satisfies this condition. And by definition of a set, this R must be a member of this R. So we conclude this one. Okay? So let me repeat. If R is not a member of R, this R satisfies this membership condition, meaning that the X belongs to R. Here X was R, so R belongs to R. Right? So we get this one. What about the other case then? Suppose R is a member of R. Okay? So what happens here? If R is a member of R, then it has to satisfy the condition. So R must not be a member of R. Okay? The only condition that makes X to be in R is when X is not in X, right? Okay? So if R is in R in this set, that means R satisfies the condition here, meaning that R is not a member of R. In either case, we got the contradiction. Now, there are actually many examples of this kind. So you can think about a container that contains all containers that then contain themselves. Okay, similar to the Barber's case, you can say. In computer science, the compiler that compiles only those which do not compile themselves. That's also a paradox. Okay, you can imagine a lot of these things. So there's something called axiomatic set theory that was born to avoid this paradox. And it is defined in terms of formal logic. And unfortunately, we are learning the formal logic now, so we don't have time to go over this. But once you learn some basics of logic, and if you happen to know more about it, try to look for the axiomatic set theory and find the axioms there to avoid that avoid this kind of paradox. Okay. All right. So the next one is about set operation, and okay. So if you go to 355, there's a lot of formal language, automata theory, where you're going to use this kind of set operation. Union, what is, so maybe if you have some intuition, that's okay, but I also want you to understand the formal definition, because intuition may go wrong in some corner cases. So A union B is defined formally as a set of X such that X is a member of A or X is a member of B. A intersection B is similar, but X should be a member of both A and B. And A set minus B is a set of X such that X belongs to A but does not belong to B. There's another thing called power set. And okay, this power set, okay, good. So the power set is a set of all subsets of S, and typically denoted by 2 to the power of S. So let's practice this example. So what is A union B? Here. First, how many elements will be there when you do A union B? How many elements will be there in A union B? Nobody knows? 4? Okay, so let's see. According to the definition, you have to pick members from each of their set, right? So A has 2 elements, 1 and 2. B has 2 elements, but these elements are different from the elements in A. So it has singleton set 1, singleton set 2. So there will be 1, 2, singleton set 1, singleton set 2. Okay, so there are 4 elements there. What about A intersection B? Empty. We don't call it 0 because 0 is a number, but we are talking about a set. So this is empty set. Okay, also denoted by this symbol. Okay. What about A set minus B? 1 and 2 is in A, okay, and they are not in B, so A minus B is actually equal to A in this case. What about 2 to the power of A? To the power of A. So 2 to the power of A is a set of subsets. This is a set, okay? And you have to enumerate all subsets of A. How many subsets does A have? How many subsets does A have? Empty set, right? If you don't choose 1 or 2, then 0. If you choose 1, that's another case. If you choose 2, another case. If you choose both 1 and 2, that's another case. So you will have 4 subsets. And you can check, using the definition that I provided before, each of this element here is a subset of 1, 2. Okay? In other words, you can check empty set is a subset of 1, 2. Okay? 1 is a subset of 1, 2. 2 is a subset of 1, 2. 3 is a, there's no 3. 1 and 2 is a subset of 1, 2. Okay. All right. So now what about 2 to the power of b, or the power set of b? It's similar, but you slightly different thing is how you write the elements. So first, empty, you don't have to choose anything. But if you happen to choose the singleton set 1, then you have to choose this one. The second one is this. The third one is this. Okay? All right. Now let's talk about other things. So suppose you have m element, okay, in the set. How many subsets can you generate? 2 to the power of m, right? Okay, so if you have 1, 2, 3, let's say you have up to m, then how many subsets will be there? Okay, so you can enumerate one by one, the empty set, or 1, okay, or 2, okay, or singleton set, and 2 element set, and so on and so forth. This is actually very tedious to do. So I want you to actually understand what is going on. So there are actually multiple ways that you can count. How many subsets are there? Each subset will either contain this each element or not. So there are 2 choices, right? So each element can either pick 1 to be in the set or not, or 2 to be in the set or not, 3 to be in the set or not. So there are actually 2 choices for this guy to be included, 2 choices for this guy to be included, 2 choices to be, this guy to be included. If you do this counting, this will be 2 to the power of n. Okay. Another way to view this is, suppose you look at this as a table. Okay, 1, 2, 3, 4, 5, up to, say, let's actually say 5. Okay, then there should be 32 subsets. You can count this as a membership. So 0, 0, 0, 0, 0 means none of the things are in the set. That means empty set. If you say this one, so each entry is either 0 or 1, meaning that this one represents the set that contains only 1, but none of the others. If you write this one, then you have 1, 3, because 1 is counted, 3 is counted, and the others are false. Okay. Okay, so I glued up that page. So in general, if you have m elements, then there are 2 to the power of m subsets that you can form. Okay, any question up to today's material? Okay, so then let's close and let's open the cooperative.